Hello everyone. In this video we're going to be taking a look at systems again, but with internal forces. So remember, one of the problems of using the systems approach is it doesn't give us any information about the forces that are internal to the system. But we can mitigate this by pairing the use of the systems approach with analyzing individual objects. So we'll be taking a look at this example again. Remember, in this example where we have the cart of mass 2m and the hanging mass of mass m, the tension force acted on both objects, and it acts the same on both objects because it's the same string. But we weren't able to analyze it because we were ignoring it by looking at the entire system and as how it moves as a whole. And so we'll work through and solve the acceleration of the system again, just using the systems approach. So while the tensions were internal to the system, the gravitational force on the hanging mass is responsible for accelerating the system. Remember, the gravitational force and the normal force of the cart ended up canceling out and they don't affect the acceleration of the overall system. So we get that the acceleration of the system is just m times g divided by the total mass of the system, which is going to be 3 times m. So we get m times g divided by 3m, the m's cancel out, and we just get that the acceleration is g divided by 3. So to figure out the tension force, we actually need to take a look at the objects inside the system. So we're going to work through the 5 steps of solving free body diagram problems. We're going to start with the cart. And we see that the cart has up and down forces of normal force up, mg down, and it has this tension force to the right. But we're ignoring friction, so there isn't any leftward force. So the free body diagram here is relatively simple. We don't have any angled forces, so we skip straight to looking at the sum of forces. And I'm going to ignore the vertical components because I know that they cancel out. But the horizontal component, we get that the tension force is the net force, and that's equal to the mass of the cart, which is 2m, times its acceleration. For the hanging mass, we see that we have that downwards force of mg and an upwards force of ft. And we know that the downwards force should be bigger than the upward force because it's accelerating in the downward direction. And there are no horizontal forces, so we can actually skip straight to the sum of forces in the vertical direction. So we get the upwards force of tension minus the downwards force of mg should equal the hanging mass's mass times its acceleration. So this is now convenient because we're looking for the tension force, and by analyzing the forces on each object, the tension force pops up in the Newton's second law equation for each of them. So it gives us a way to solve for that tension force. Since we've already solved for the acceleration using the systems, and we know that they're accelerating in unison, we can simply plug in the value g over 3 for either one of their accelerations and continue to isolate the problem for the tension force, and we should get an answer. So plugging this acceleration in for the cart, we get that it's 2 times m multiplied by g over 3. So our tension force should be equal to 2 times mg divided by 3, or 2/3 mg. Doing this for the hanging block, we should get the same thing because the tension should be equal. But it's a little bit more complicated, but not so much so. So we're going to plug in the acceleration g over 3 in for the acceleration of y. And we get that the tension is equal to m times g minus m times g over 3, or 1/3 m times g. So if we take a whole mg and subtract 1/3 of an mg, we're going to get 2/3 left over. And you can do this with simple fraction math. So our answer when solving for the vertical is the same as solving for the horizontal. So we get 2 times m times g divided by 3. So to reiterate, the process that we followed is we used the systems approach to figure out what the acceleration is, and then we looked at each individual object, we wrote a Newton's second law equation for each individual object, and we plugged the acceleration we found from the systems approach into the sum of forces for each individual object, which allowed us to solve for internal forces. And that's it on this video, going over how to find internal forces using the systems approach as well as the individual object approach. Thanks for tuning in, and I'll see you next time.